il n'y a pas de. C'est pas grave.
Il n'y a pas de.
On va poser de.
La bouteille, ouais, c'est pas top.
C'est pas grave.
Je peux faire un petit test avant?
Non, non. Maintenant.
Ah, justement, ça c'est pas le cas. Parce que là, on est
Ah bon, c'est bon, on s'en fout.
En fait, celui-là, il a pas de siège.
C'est quoi ça? C'était mal idéal.
Ok.
Hey.
You are sharing?
Yeah, I am.
Ça marche pas?
Non.
Non, c'est sûr.
Je sais pas, c'est un truc qui est tellement vieux.
Thanks for coming. Looking forward to the talk.
Oh, no, thanks for inviting me.
On va mettre un autre.
Ouais,
It's not very far from home.
c'est qui, ouais, tu me
It worked yesterday.
Yeah, I remember the same issue yesterday.
Okay, good.
Okay.
Okay, good. Just how should I speak? Like 50 minutes? Or...
That sounds about right.
Okay,
Yeah.
okay. So if I shouldn't go over time, or if I really do go over time,
Yeah. Yeah. I mean, anyways, the thing we have afterwards is the business meeting, which is
it's my classes. May not see you.
Okay.
Because that is for reading, so yes, so reading.
Okay.
Ok, magnifique.
Oui, mais c'est a good success.
Yeah.
So
I'm,
Une photo. Faut que tu jettes. Non. Moi je viendrai juste pour le poulet. Poulet.
The wrong week.
C'est comment? C'est le son que les gens de. Il est où Antoine là?
Il va récupérer son pré de thèse.
Ah mais oui c'est vrai.
Cet après-midi. Il doit être en train de prendre des gens.
Ça marche? Non ça marche. Ah moi c'est pas allumé. Yes?
I lost my phone in this venue.
What's the brand of your phone?
It's Oppo. It's on the back side is all blue.
All
It's,
blue, okay.
blanking blue.
We can send a message to the...
Okay.
You
Or
lost it in this room?
Yeah.
Maybe we can.
Maybe at the
call-
end we can do a little
Okay.
tour and
And
I
maybe
will...
we can call you.
Call me.
Yeah.
I don't have any phone.
In order that it rings, and maybe we can hear it.
I
No,
sent a
if it
message
rings.
to
Okay.
You've
been there.
Yeah. But I guess you already looked...
Yeah, so the part was fun. I was actually on sabbatical this year out in Berkeley and Stanford, so I spent a bunch of time thinking about LLMs there and excited to go back home.
Thank you very much.
No problem.
Putain mais après ça comment je peux dire que je veux du poulet?
Après, Maël, il propose de l'appeler, il dit pour ça. Il a dit, j'ai pas le téléphone, il est con quoi ce mec. Alors que c'était une bonne idée.
Oui.
Moi aussi, je me suis dit que
ça, je suis
c'était
passé
bête.
pour un abruti, mais.
Bah ouais, je sais pas pourquoi il était en train de con quoi ce
Mais
mec.
parce que moi aussi j'ai compris comme...
Ah mais il est
Genre si je le
silencieux.
trouve, je t'appelle, tu vois, et un truc comme ça quoi.
Ah.
Moi je sais pas comment il a... Mais on va...
J'ai battu le rappel, mais il en reste encore pas mal à...
À côté.
C'est énorme.
Vous allez voir Roman pour lui demander. C'est Roman, celle qui est...
Peut-être qu'ils ont une place dans mon coin. Do you want a mic?
Sure. Yeah, sounds good. Hey, how are you? Yeah, you can come.
No, to make sure that there's the Zoom link for the business meeting because
Oh, sure. Okay.
it doesn't have it or something.
Okay.
Just that.
Okay. Sounds good. All right, everyone, let's get started. Okay, everyone, let's get started. So I'm very happy to introduce Francis Bach, who will be giving our first keynote lecture. So Francis will be talking about optimization and machine learning, which is a perfect talk title for someone who's an expert in both. So I'm thrilled to get a chance to hear him speak, and thanks for accepting our invitation. Please take it away.
Okay. So thanks, Anchor and Nika, for the invitation. So today I'm going to talk about optimization machine learning, and this will be part work from my group and part work from the community. And the talk will be divided in two parts: one on convex problems, where things get quantitative, and one on non-convex problems, where things get less quantitative. And I think it's a good opportunity to reflect on the achievements from the convex side and the progress and need for further progress in the non-convex side. So to set the context quickly, okay, so we live in a world of data, and not only in social media, but all over industry and all over sciences, both from bioinformatics, humanities, climate science, you name it. And for the last many years, like 30, 40 years, there's a need to process that massive amount of data. What is a bit new in recent years is that the models that we train are being used very far away from their training scenarios and even used by the general public. And this has led to a series of hypes, okay, starting from maybe 2010. There was big data science, machine learning, deep learning, AI, LLMs. And how should we react to that? So I think the core community is really immune to that hype, which I think is a good thing. But we cannot really leave out the question of positioning of learning theory. And throughout my talk, particularly toward the end, I will give examples from the topic at hand today, which is optimization for machine learning. So let's start. So we're going to look at the classical parametric supervised learning, where I have n observations, xi, yi. Xi can be an image, yi a label on that image. They live on very generic spaces x and y. I have n of them, and I'm going to use prediction functions, which have two parameters, the input and the parameter vector of my model theta, and theta leads in RD. So classical examples, okay, so linear predictions where you have some feature vector phi of x and your linear and your parameters theta. And this is like still used quite a lot. This used to be used a lot in advertising, but there's still like many areas where you need linear predictors. But the reason for all of the hype is more like neural networks. So if you want to predict like cats and dogs, but it goes like, of course, much further, then you need to use nonlinear models, nonlinear the parameters. So the standard multilayer perceptron, multilayer like feed-forward neural network is you start from X, you apply some linear function, take some activation function sigma component-wise, and iterates. Okay, so there's various forms of linearity in that model, but globally it's non-linear. How do you fit this? So this is typically now fitted using minimizing the regularized empirical risk, where you have a sum of two terms. The data fitting term, we have a loss between your label, yi, and what you want to predict, and some regularizer typically used to avoid overfitting. So throughout this talk, which is about convexity and non-convexity, I'm going to assume the loss is convex. Okay, so think of the loss being the squares if you do regression, or the logistic loss if you do classification. And of course, you don't need to only use like output functions in R. Okay, you can do multi-class, and you can. There is in that setup a lot of other convex losses. But the loss is convex in many applications, even in the deepest, latest applications. The loss remains often convex. The problems will come from the edge, which may not be linear in theta. Just remember as well, and this is not the focus of the talk so much, is that the goal is not to do well on the training data. So here, optimization is just a mean to an end. The goal is to do well on unseen data. And as soon as you say, like, you have two types of data, training and testing, you have to assume some form of relationship, okay? And then the most traditional one, which I'm going to use later in the talk, is of ID, okay? So both training and testing data come from the same source. Clearly, it's never true, but it's typically the first idealization that people come up with. So at the end, because you need to do well on unseen data, the expectation over the test data, all this machine learning problem is both statistics and optimization. So today we'll focus mostly on optimization, but keep in mind that it's just a mean to an end. All right, so when do you get a convex optimization problem? When sufficient condition in that H is linear in the parameter, so this is like the classical example, because the loss is convex. So if you take a non-convex loss, then this will not be the case. So this has led to a nice wave of algorithms and guarantees, okay? You get algorithms typically gradient-based. So for a convex problem, if you are careful enough, you follow the gradient, you're going to end up at the global optimum, okay? And not only this is going to work well in practice, there is guarantees, both in terms of runtime and in terms of prediction performance on unseen data, which are quantitative. So this, what I call the golden years of convexity, okay, which started maybe with the SVM years in '95 up to recently. So here I put 2020. It's quite arbitrary. Convexity did not contract COVID. And there is still like a lot of work in the area. But clearly, in the last 5 years, like the non-convex problems have become really prominent. And today, I'm going to focus on like a large-scale learning with like stochastic gradient type of problem, online learning. But there is like, I could give the exact same first part of the talk with a different area. Okay, if I use like a low-rank model like sparsity-based optimal transport sampling, and many of the areas of learning theory have benefited from convexity as well. So let's look at algorithms. So this is the classical like problem where I'm going to use the fact that my cost function is a finite sum or a finite average, and this is like the classical like I'm going to minimize the function g. And each of the elements of the finite sum is the loss from one data point, okay, plus the regularizer. So here there are many variations. I could use a mini batch, okay, but for simplicity, I'm considering one element in the sum. So the first algorithm that dates back from long ago is gradient descent, where it's iterative. I start from a point. So here, this is like an example of logistic regression in 2D, okay? So it's a convex function. It has a unique global optimum, and this is high values, low values, and gradient descent will start from a point which is typically random, often 0 in practice, and you go down the direction of the negative gradient, which is orthogonal to the level sets, but contour lines, and you do a big step of length gamma, and you iterate. As you see here, on this simple problem, you make very quick progress toward the optimum. And so this is all nice in terms of number of iterations, but it's well known that each iteration requires to complete the full gradient of G, which is the average of all gradients. So to make a big step, you need to have a look at all of your data set, and this is clearly a problem when n is like 10 to the 12th. So this has led to the prominence of stochastic gradient descent. Okay, and so here first, it's a very bad name. Okay, so I didn't choose it. I didn't know who chose it, but it's a bad name because it doesn't go down. Okay, so on that simple example, okay, I start from one step, and I don't take all of my gradients. I just take one of them. Okay, so here there are also many variations. Should I cycle? Should I take sampling with replacement, sampling without replacement? So here I'm going to focus on I of t chosen with replacement. Okay, I chose one function. Okay, so the expectation with respect to I of t, because I select I of t uniform, is the finite average. So I guess this update is unbiased, but it is random. Okay, and so sometimes it goes up, and on average it goes down. So the key here, which I find really amazing, and this dates back from the 50s, is that the variance of the noise does not need to go to 0. So if I replace unbiased estimate by potentially biased estimate, the bias has to go to 0. Otherwise, I may send the estimate far away. Constant variance is good enough. All right, but the issue here is that the number of the complexity of each iteration is going to be very fast. Okay, we're going to oscillate a lot. Is there a way to do better? So in the convex case, there is a sequence of work which we worked on with Nicolas Leroux and Mark Schmidt in 2012, and then there was like follow-up work by several people in the community. The idea is, can you preserve the small time complexity of each iteration O of 1, access to gradient, but preserve exponential convergence, which you have if you do the full batch gradient. It turns out this can be possible. So here I'm describing the saga version with Aaron DeFazio and Simon Lacoste-Julien, where you start with the unbiased estimate of your gradient, okay, unbiased with respect to I of t, and you add some terms whose goal is to reduce variance. This is a classical idea in simulations, Monte Carlo simulations, which we adapt here. So here, what is YIT? YIT is some version of the gradient of function I at time t. Okay, so since you compute gradients one after the other, one at every iteration, you store them. Okay, and YIT, that stored value, which you update at every iteration. And what we do is we subtract the gradient from before that we indexed by I of t, and we add the average gradient. The effect of this is that the expectation with respect to I of t remains 0, okay, because this is the expectation of that term in that term. So the update remains unbiased, but it turns out that the variance is being reduced, and the variance goes down at the same speed as you converge. So at the end, you get things of that kind, okay, so where you converge, you don't always go down, okay, but you converge quickly and also at exponential rate. Okay, so there are many variations of this. So here, a big caveat is that you have to store gradients, okay, and so this was alleviated by the work by Johnson and Zeng and colleagues by SGRG, which allows you not to store gradients. So in terms of running time guarantee, this is what I want to focus on in this first part, is that for simple problems, let's say like regularized logistic regression with a linear model, then you get guarantees which are quantitative. Okay, you can compute condition number. Essentially, this is the ratio between the norm of your data over the regularization parameter, which you know. And this is known to characterize the convergence of gradient descent in the strongly convex case. So for gradient descent, the number of access to gradients will be, for each iteration, I have to look at all gradients. So I pay over a value of n, and then the convergence time will be the condition number. Okay, I pay n times kappa, and I have exponential rate, hence the dependence in the log of 1 over epsilon. So this is gradient descent. The optimal version is accelerated gradient descent by Nesterov, where you replace kappa by square root kappa. Then SGD, okay, so SGD is known to work well in that setup. You're going to lose the factor n because you access a single gradient. Every iteration is n times less costly, but you lose the logarithm. Okay, so if you want to get very low epsilon, it's going to take quite a while. Again, this one is also optimal if you don't have a finite sum. So if you do a single pass SGD, this is the optimal behavior. So what we propose is this algorithm, which is almost as simple as SGD, gets you something which is not the product of n times kappa, but n plus kappa. Okay, so when kappa is of order of n, which is typical in the learning scenarios where the regularization parameter goes down to 0 as you get more observations, then the gain is substantial. And it does, in fact, improve both on SGD and even on accelerated GD. So it does break lower bound, but break, of course, in quote, because it comes with extra assumptions. And the assumption is really finite sum. Okay, so if you leverage the fact that you have a finite sum and not an expectation, you can do much better. So this has been built on by many people. Okay, so you can accelerate this. Okay, Alan Nesterov, and there's nice work by Shai Schwartz and Deng, Nintenda, Lan, Ling, and colleagues. Essentially, by a simple modification, like a combination of variance reduction and Nesterov acceleration, you can replace this n plus kappa by n plus square root n kappa. So essentially, when kappa is large for a difficult problem, then you get an improvement. And it turns out that this becomes optimal. This is optimal in what sense? For any technique that will combine linearly gradients which you sample one after the other, you cannot beat this. Okay, it's a classical lower bound. We're showing that we now reach, we as a community reach this matching upper and lower bounds. If you don't like finite sums because you care about online learning or single pass SGD, there are extensions, okay, by I forgot the name, but probably Sarah, Spider, and Storm, okay, which applies in the sequential setup. Which also have guarantees beyond convex problems, but stay tuned. Those guarantees, okay, like most guarantees in non-convex problems are, let's say, questionable. Finally, there are some extensions. Okay, so finite sum appears in many areas. Okay, so there is min-max problem, variation inequalities, game theory, and this can be extended as well. And if you want to look beyond a single machine, it's also a possibility to do that. And many people worked on it. You can look at our own work and the references we provide there. So this is a nice IRA. And the key here, how it relates to the next part of the talk, is that there is a nice exchange between theory and practice. Okay, so maybe 10 years ago, maybe 15 years ago, or 10 years ago, you would write a paper, design a new algorithm, test on benchmarks, and it was doing quite well, and as well as the state of the art. Okay, and at the time, linear models were the state of the art, so it was really a good match between theory and practice. And even better, the bound that we propose, they do match performance. Okay, so this is the wishful thinking. Okay, so this is time in the x-axis, distance to optimum in a logarithmic scale. So a line means exponential convergence, and you can compare the bound which I've proposed. Deterministic looks like a line, a staircase, because every time I need to make an improvement with full batch gradient descent. I need to look at my entire data. So while I read data, I don't make any progress. I get the staircase effect, but I get a line because it's linearly convergent. Stochastic gradient in green will start to make progress at the first iteration. So it goes very quickly, and then it levels off because this is not exponential. And the new techniques should have the best of both worlds, start quick, and then get also a line which is even steeper than the deterministic one. And this is from the bound, essentially, and this is what you see in practice. Okay, so here this is the deterministic methods on top there, SGD in blue and green, and SAG, which is one of the versions that we have worked on. So here you see matching between theory and practice. You get improvements which are suggested by theory, in particular non-uniform sampling. So if your functions, fi, are not all uniform in the way they vary, you're better off by sampling the ones that vary most more frequently. And this can be done. They are matching upper and lower bounds. And I think this is, at the end, starting to reach the same level of stability and robustness that we get from numerical linear algebra. Okay, we're not there yet, okay? But I think this is like getting closer. But the question is, what about deep learning? Okay, so how can we extend all that to deep learning? I need to drink because it's going to be difficult. All right, so the idea here is that for convex problems, the picture is reasonably satisfactory. Okay, I have quantitative guarantees, algorithms which are efficient and that work well in practice. So what about deep learning? Okay, so here, now for the last part of the talk, I'm going to focus on the statistical analysis of deep learning. So first, I'm going to reduce a lot the scope. Okay, and as you will see in the next like 5 to 10 minutes, the scope will be reduced like a lot. Okay, I'm going to lose a lot, and the question will be how you can gain back understanding after you have like simplified the problem so much. So I'm going to consider the simplest like deep learning model, like a multi-layer neural network feed forward. So X remains the input. I'm going to have like input weights, maybe a second layer, and et cetera, et cetera. So here, I'm not going to consider the ResNet transformers from Bach, which are which work very well in practice. I'm going to focus on the simplest problem. So what are the two main difficulties? They are associated with the fact that in practice, the number of neurons, okay, the number of parameters in my model will be very large. And when I mean very large, far larger than the number of observations, okay? And this is creating some difficulties, both in terms of algorithms. It may be slow to learn that many parameters, and also in terms of statistics. How well do I generalize on unseen data when I have a lot of parameters? Okay, those are the two main difficulties. I will focus mostly on the first one, the non-convexity of the loss, but briefly mention what you can say in terms of generalization. So here, what looks like a potential curse happens to be a blessing. Over-parameterization will help us at least help us optimize. This is true empirically, and the next part of the talk will try to convince you that this is also, there's a reason for it that I'm going to explain. So first, what can go wrong when you go non-convex? This is a nice paper by Lee and colleagues. So this is like, I forgot which model, but you take like your neural network, you look like at a random 2 directions around the optimum, this is what you get, okay, in terms of profile. Okay, it's not really like your nice ball-shaped convex functions. Okay, so you have like lots of like plateaus with 0 gradient, not nice. You have some like saddle point, okay, not nice. You have tons of local minima, okay, and you have maybe one valley which is going pretty well. Okay, so when you go non-convex, anything can happen. And the beauty of convexity was that it was a very simple assumption that was covering still a broad range of problems, which was enough to do everything. As soon as you go non-convex, it's too large. There are tons of lower bounds showing that if you have a non-convex function, which is just Lipschitz continuous, you can't escape the curse of dimensionality and get exponential dependence in dimension. So anything generic will not fit, and you need to look really at the problem at hand, what happens when you have a neural network. All right, so first, algorithms. Algorithms remain the same as in the convex case, okay? You still have a finite sum, simply H is much more complicated than before. And the classical algorithms, AGD, is being used, typically with momentum, okay? So you do a stochastic gradient step and you keep some momentum term. So this one has global guarantee in the convex case and only local in the non-convex case, okay? There's a nice review paper by Liambotou and colleagues. And so here, I would like you to reflect on those local guarantees, okay? So I've worked on those, so I include myself in the criticism I'm going to give. They are not good, okay? They are, at the end, if you look carefully, this is the average of norms of gradient, okay? All the trajectories in expectation is going to 0. We are very far away from the algorithm converges to a stationary point, okay? And this is hard to beat, and this shows that those local guarantees are good to have, okay? But they are not sufficient. So this is for LGD. Of course, there is Adam, okay, which has been used a lot, and this is like building on Adagrad, which was a bit before, and the idea is to rescale the updates. Okay, you divide like the gradients, the local the gradients like this by norms of previous gradients. Okay, this has some nice reconditioning effect. Also, it has global guarantee of the convex case with several papers, but only local guarantees otherwise. There are other like newcomers, like Muon, which you may have heard of, which is like a bit different, but similarly, you can define it in the convex case, analyze it in the convex case, get guarantee in the non-convex case, but those guarantees are always local. So the question is, why does it work so well for deep models? Okay, so again, those local guarantees do not tell you much about the reasons why it works. In particular, those local guarantees can get you a bit anywhere. Can get you there, zero gradient, can get you there, zero gradient, unlikely, but zero gradient, can give you any of those local minima. So how do we leverage the structure of the problem to get guarantees? All right, so let's simplify the problem even more, okay, and take a single hidden layer. Okay, so this is like the simplest non-linear model in the parameters. So now I have one hidden layer neural net, okay, where the input is x. Okay, I have some input weights, which is a matrix of size d, if d is a dimension of x times the number of neurons. And then those are my hidden neurons, and I'm going to combine them with the output weights θ2 to get my function h. And the key here, why we are going to reduce only to a single hidden layer, is because you can notice that the prediction function is of that form. It's an average, okay, or sum, if you prefer, of functions which have their own parameters. So every atom Psi of Wj has its own parameters. Okay, each of them corresponds to one hidden neuron. If I take the first one, it has input weights. Okay, the jth column of θ1 here, and it has the output weight θ2. So Wj is the concatenation of θ2 of j and the jth column of θ1. And what we have is that the predictor is a sum of functions, okay? But each of them have their own parameters. If I go with one more layer is not true anymore, okay? Because there will be like a sharing of parameters of the first layer, okay? So we need, at least for the results I'm going to provide here, we need only a single layer. We also need convexity of the loss, okay? So we need the loss R here will be the classical loss, the expectation over the training or testing data. It doesn't matter here so much anymore. It has to be convex in H. And even in the deepest networks, R is convex because L is convex. It can be the cross-entropy loss or the least squares. So what is the main insight? So it's very classical. It's not ours. Okay, we'll show references in a moment. Is you can see this big sum over there as the integral over some measure. And that measure is the empirical measure of the neurons Wj. So now, from now on, I'm going to call the Wj's particles, because this is the classical terminology in physics. So the idea of the mean field limit is to take this set of Diracs, and if you add more and more Diracs, okay, and then it's going to behave like a density of neurons, and the idea will be to replace individual neurons by their density, and then we're going to use like a partial differential equations on the density. So this is the idea of the mean field limit. So this has like a long history in statistics and machine learning, and the idea here is that we have essentially linearized the problem or convexified the problem. Why? Because I went from a very non-convex function, very nonlinear function in Wj, because I have like a product, I have a sigma here, to something which is linear in my parameter mu. Okay, so this leads to the first idea. Oh, now I have a convex problem in mu. How can I solve it directly? The catch here is that mu is a set of all measures, which is infinite dimensional, for which it's hard to do optimization with classical computers. And one idea is to use like methods which are dedicated to learning on measure, which is like Frank-Wolf techniques or conditional gradient. This leads to some bound, but it's not really tractable. It's not what is used in practice. What is used in practice remains gradient descent, which is which is backprop, okay? So you still preserve your individual neurons, okay, form the cost function and go down the gradient, okay? So three questions arise then. What is the limit when M gets large? We want to study the potential benefits of over-parameterization. Does it converge to a global minimizer? This is what the idea of adding more neurons. And does it predict correctly? So first look at the algorithmic limit. So this is like a joint work with Lene Shiza from a while ago. So we have a general framework which goes beyond just neural networks, okay? As soon as you want to minimize a convex function of the expectation of the measure mu, okay, then you can minimize it by forming the same cost function replacing the expectation by the set of particles, okay? And we're going to study the gradient flow. Okay, so here, extra simplification. We're not going to use gradient descent. We're going to use the gradient flow. And in a sense, the gradient flow on W, which is the matrix of all neurons. The factor M here is just to make sure things are normalized, because I have to, for this to be equivalent to this, I need to divide by M, okay, so that the empirical measure converges to a density. And now I need to put the M to avoid like a bad scaling of the gradient. And why gradient flow is correct, so this is where I'm going to hand wave a bit, and I'm going to hand wave a bit like in the next few slides as well. It's a good way to idealize single pass AGD. In fact, the original proofs from the 70s or 80s for AGD were using gradient flow. Okay, so when you take AGD and you let the step size go to 0, you don't converge to a stochastic differential equation, you converge to the gradient flow. Okay, and this is what has been used for proofs. If you do multipass AGD, which is common in practice, then you end up with an approximation of the full gradient descent on the empirical risk. And there are papers that analyze this, but let's focus on single pass AGD, which is quite modeled by the gradient flow. So first, the limit. So it has a name which is called a Wasserstein gradient flow, which is a flow over measure for a specific metric based on optimal transport. And this was like highlighted by several authors, starting from Nintendo and Suzuki and many others. So it has a name, okay? You can derive a partial differential equation for the measure mu as a function of time, which is a classical like transport equation. I won't give details, I will just give you the outcome. Okay, the fact that it has a name is good. What you really want is that the thing that had a name has good properties. And it's essentially what Lenaik and I worked on like a while ago. And this is our informal theorem. And this is, I want you realize that when I was presenting my table with like condition numbers and convergence guarantees for the convex case, there was nothing hidden, okay? There was no like hidden assumption, strong convexity, which is pretty strong, but still the assumption was very clear. Here there is quite a significant number of regularity assumptions. And the informal theorem says that if you have more and more neurons, okay, so the Wasserstein gradient flow, the limit when the number of particles go to infinity, will converge to the global optimum. So of course there is some conditions. Okay, so this applies to the one in the layer neural network. It's a classic mean field which is common in statistical physics, but it needs two ingredients. Okay, this is not true in general. Okay, if you take a problem like this, okay, and you put particles and optimize, you won't always get the global optimum even when the number of particles is very big. Okay, there are conditions, okay? And the conditions we came up with is first homogeneity of the function psi and a good initialization. And of course, convexity of the loss. Okay, so this is where we need convexity at one point. So homogeneity, this is like, there are various ways, but let's make it simple. If you have the Relu activation, which is the max of u and 0, it's one homogeneous. If you multiply u by a constant, you multiply the output by the same constant. And this is required for our separation condition. And you need to initialize neurons in a quite diverse way. Okay, so uniform Gaussian, so uniform on the sphere, which is what people do in practice. And then once you have those, plus some regularity conditions, you get the informal theorem, which I'm mentioning here. For illustration, before illustrations. So here, it's in a sense a blessing of over-parameterization. Once you get to a number of neurons which is very large, you're not going to be stuck in local minima. There are local minima when m is small, but they still exist when m is large. But when you start from the correct place, which is like density, like positive density everywhere, then you won't get trapped in those local minima. Of course, it's only qualitative. So here, and I'll come back to that later, there is no notion of how fast it goes in time and how big the number of neurons needs to be. So illustration first. So you see like in 2D, okay, it's not a very big data yet. So in dimension 2, this is I'm going to generate data from a neural network, okay? So here, this is output weight, no intercept, and I'm plotting the direction of the neurons. And I'm generating the data from 5 neurons, okay, and I'm plotting the direction of those 5 neurons. So if my neurons here in red are converging to the dotted line, it means that I've estimated correctly my network. So 5 neurons on the left, 10, 100. If I start with the number of neurons which I need to optimize things perfectly, if I get no local minima, I should converge. In fact, sometimes it does, sometimes it doesn't. Okay, this has been like noticed by many people that you get stuck when you optimize neural nets. Our results suggest that if you take a lot of neurons, this should not happen. Okay, and indeed, like in this simple illustration, it doesn't. What remains open is in between. Okay, when M is not infinite, what's happening is still like reasonably open. What I want you to notice as well is that the path of neurons is not really like a straight line. Okay, they evolve and then they make big turns. Okay, so the dynamics remains quite complex, but they all end up in the correct places. Quickly, on overfitting, it's not the topic of the talk. Okay, I just want to highlight that this unfortunate common wisdom that we see everywhere, that a model with many parameters will not generalize well. Okay, in particular, the number of parameters is higher than dimension. So this is like a wisdom that we see everywhere. I don't think it's a good wisdom. What really matters is not the number of parameters, but this aggregated magnitude of those, like a norm, provides a finer control. There's tons of work about it, many references about it, but there is one I prefer, which is my own book, which I really encourage you to buy, okay, which provides like examples, but of course, clearly, I'm not the only one there. And since you need some control over the norm, it turns out that that control is provided not by imposing the norm, but by gradient descent itself. And there's a nice series of works on the so-called implicit bias of gradient descent towards minimum norm solution with the proper norm. So this was started by Gunnarsdottir and colleagues. Nice work by G. and Telgarsky, and we have worked as well on it with NIX. So essentially, often for those problems, particularly if you use like a logistic loss, the iterates diverge to infinity, but the direction along which they diverge corresponds to a minimum norm solution for a particular supervector machine. And this leads to situations where, although you overfit, it is not catastrophic. You won't like do very bad on test data, and there is nice notions of benign overfitting, and a nice paper by Peter Bartlett and colleagues. So there's a big area in how to make sure that you generalize correctly. It's not the focus of today. The focus of today is how can I improve those qualitative guarantees? Okay, so what we are looking for, okay, is how can I get a handle on the time t I need to optimize, okay, and the number of neurons m which I need to get global convergence. So after like 5 or 8 years working on that, I'm sorry to say that we have not really succeeded, okay? It's too hard. Okay, in general, okay, so many people have tried. It's too hard for many good reasons, okay? First reason, dynamics are complex, okay? You often see this so-called like saddle-to-saddle dynamic where you go from one point to the other in a way which is very, very hard. It's relatively easy to predict in simple models, but very hard to characterize in the general case. There are also like simplicity biases, is that those methods based on GD and wide neural nets may underfit, okay? They get two simple problems. So if you want, for example, to get overfitting with a single hidden layer neural net, for regression it's difficult, okay? Because you get stuck often in very simple functions. So sometimes simple is what you want, but sometimes it doesn't, and I refer you to the nice paper by Shine colleagues and Boursier and Flammarion to look at this. So there's no generic answer, okay? It doesn't mean we have to stop there, okay? So we need to find like simplifications, okay? And now the goal of the last part of the talk will be to look at simplified models and architectures, so that models for the data and architectures for the learning method, which are still relevant. Okay, so here we can argue forever about what relevant means, but since I am on the stage, let me give you my take on it. So I think I have like 3 requirements which I would like to have. First disclaimer, most of my work does not satisfy any of those. Okay, it's just like a good target to have. The first one is, of course, being quantitative. Okay, so the goal is I'm simplifying the problem to make quantitative statements. So here I don't care so much if they are asymptotic or non-asymptotic. Okay, I think this is the first requirement. If you simplify, this is to get like a more finer analysis of the problem. But then, does it have an impact on practice? Okay, so can it be run on a computer? I still believe this is interesting to have models which can be checked empirically and can be valid beyond the model assumptions. Okay, so I work on a linear method. Maybe I can get something, a behavior which is also valid on more complex problems. And finally, this is like to be the gold standard, which is very hard to attain, is that what does it mean to have understood the problem? It's unclear. Okay, to me, one common way is if I get it, I can propose improvements, and those improvements should work on a new problem. And this is something which is very common in physics and mechanics. Okay, you're not able to understand really the full picture, but you understand some parts, and those parts are enough to get a global improvement. All right, so let's look now at some of the ideas which have been proposed. The first 2 were quite generic. Okay, let's focus on that particular framework, gradient descent for wide neural net, and the other ones will be more specific. So the first idea is to add noise to the model. Okay, there was a nice session this morning on sampling. Okay, so you do gradient descent, this is your empirical risk, and you add some Gaussian noise. Okay, the Gaussian noise has a variance which is the same magnitude as the step size, and you have some temperature tau. So at 0 temperature, you go back to gradient descent, and at high temperature, you add more and more noise. So this was like analyzed by several people. The key here is that as soon as you add some noise, okay, and the step size is small enough, you go in a world where things are a bit simpler. Not simpler, but I think the theorems are more direct. In particular, this, when the gamma is small enough, will converge to the in distribution, to the Gibbs distribution with density exponential of minus f over tau. Okay, and this is true under a wide variety of situations. No need for convexity of f for this to be true. Okay, so this allows for quantitative guarantees. The issue is the time it takes to converge. Okay, and that time typically will scale badly with temperature. And when tau gets to 0, which is what people use in practice, then you don't get this nice guarantees. Second idea is to change the scaling. So this was like a launch 5 years ago by Du and colleagues. The idea is you're going to replace with my finite average. Here, I'm going to rescale the problem by some constant. Okay, so here, why did we rescale this like this here? Is because if the psi here, Wj, have the same size, the average has the same size as well. If I multiply alpha by alpha, which is quite large, this may explode, but it turns out that when you initialize those methods with random data, you get zero mean random variables, so the magnitude will be of order, the average will be of order 1 over root m. So you can have alpha as big as root m, it's still, you won't explode. Okay, so this was really the idea in those papers. And what is amazing is really that with that assumption, they can get global linear convergence, and not only for the shallow model, but even for deep models. There's a nice industry of paper showing that you can get nice convergence. But the issue is that this is what we have worked on with Lenny Shiza and Edouard Oyalon. This corresponds to a regime which we call lazy. So why lazy? Because the neurons do not move. Okay, there is when alpha goes to 0, you can show that the neurons will move of order 1 over alpha. Okay, and so this means that there is no feature learning in the sense that you start with your initialization, which is typically random, and you move very little. So at the end, what you end up doing is learning from a model which is very close to what you started. And if you do Taylor expansion around what you started, you get a linear model. Okay, and this is exactly what is called a neural tangent kernel from Jacques and colleagues. And so here, this allows to get convergence guarantees, but you don't get like the nice feature learning approaches, feature learning aspect that you see like in deep model. And we have some work with Alberto Bietti showing that depth will not benefit, you won't benefit from depth if you do like a neural tangent kernel, but you will when you do like the classical learning. So that scaling provides good guarantees, but the guarantees do not match what people do in practice. Then you have ideas which are classical as well, when you're going to simplify architectures. Okay, so DeepNet is too complicated, okay, and there is a sequence of work trying to simplify. The first simplification is to remove the activation function. Okay, I remove sigma. So if I get, it's not trivial because I still have 2 layers. So I get theta1 times theta2, so I get a nonlinear model. And this has been studied by various papers. And again, I forgot to mention, in those slides, I probably forgot some of your papers, okay? So it's not against you, it's probably my own deficiencies. So if you want me to add it, send me an email and I can add them afterwards. Yeah, so here there is like, once you go linear, you can start to get good guarantees. And a nice paper by Pierre-Mario Lineg-Chiza recently. You can even simplify further, okay? Put some ways to zero, which is a so-called diagonal linear networks launched by Blake Woodworth, and which was worked on by Scott Pesme and colleagues. And here, the very nice thing for that line of work is that you get explicit guarantees on the behavior of optimization. You can show that depending on the way you initialize, small weights, large weights, you get more L2 implicit bias or L1 implicit bias. There's a very interesting way of seeing the problem. So very precise, very insightful, but it's very hard to extend to more complex models. Even going to the matrix case, like linear neural networks, is difficult. So this is nice to simplify, but it doesn't get you to the full understanding. Then you have the set of ideas where you simplify data models. Okay, so again, to get my architecture, I don't modify it, like a feed-forward neural net with a ReLU activation, and then I simplify the way data are generated. So there is a very nice line of work in statistical physics, okay, with Lenka Zeborova, Florent Kraskala, and many others, using like some form of Gaussian or uniform assumptions. So they get precise guarantees, but it's still in a simplified data model. Then this can be made more complex with nice work by Bietti, Brunner, and Pillot-Vivien, which also corresponds to a bit more complex model where you add like a multiple index model where you get linear function and some nonlinearity for the target network. And then there are lines of work where you're going to not make assumptions on y depend on x, but just on x. Okay, so one with orthogonal inputs and one with weak correlations, which is a joint work with Leo Dana and Lucas Pillot-Vivien. I'm going to focus on in the next slide. So what we worked on with Leo and Lucas is a simple architecture, which I've been working on for the last 20 minutes, which is a one hidden layer neural net with square loss, with a fixed number of neurons, so no asymptotics, and a fixed number of observations. And we initialize generically, no small or large initialization. And of course, we need to make some simplification, simplifying assumptions. So we're going to assume that we have weak correlations among our input. Zero correlation means like orthogonal, okay? We're going to assume that the convergence matrix is close to diagonal, but the gram matrix is close to diagonal. And this is true if you have random data and you are in a regime where you have lots of data, okay? When n is not bigger than d, it's bigger than d squared. So it's often called a very high dimensional setup, and we make no assumption on the labels. And what we're able to show is that we get some global convergence guarantees, okay, to the interpolating network, because since n is bigger than d squared, we can interpolate there. And we can do so not with m being infinite. We do so with m being only of the order of log n. So m is the number of neurons, and n is the number of observations. So as soon as m is large enough, but not too large, it's enough to globally converge. We also can characterize the time of convergence, which is of order n. So the argument is based on the classical like PL argument, which is here not an assumption, but something that we build along the algorithm. Of course, the open problem is the square is not great, okay, and we would like to remove the square. But of course, we need to put some assumption on the data generating model. Last slide. So let me now highlight some current research and open problems in the area of optimization for ML. Again, there are many other problems, okay? If your work or your area doesn't fit here, it's okay, okay? So the first one is this scaling is important, okay? So in the lazy regime, having this alpha being too large was leading to nice bounds, but not necessarily like the behavior that we want for feature learning. And this can be extended. There's a nice line of work by Yang and colleagues, the MUP parameterization, and by Chiesa and Netrapalli, feature speed, I forgot the name, I think it's feature speed, which showed that this way of scaling properly network weights and step sizes can be extended to more than one hidden layer. You can also analyze nonlinear models in a very, very nice way with recent work. Of course, going beyond this MLP is important. Okay, so deep learning has evolved from MLP to ResNet, transformers, and so on. There's also here a lot of nice work and open problem. And a new kid on the block, scaling laws, which is like a rebranding of like convergence rates. And what people have noticed is that like those two references, like empirically, when you get more data, more compute, like the test performance gets better. Okay, but they fit scaling laws, and now people are trying to catch back, okay, from the learning theory by proving scaling laws, by doing some assumptions. There's nice work by the packets here, and we have recently worked with Frédéric Kunstner on a way to put some assumptions on the data which matches real problems. So if you use text, you know that text follows the zip flow, okay, like 1/k for the case frequent word, most frequent word, and we have work on doing this, which is also recent. And we have to finish, before taking questions, on one key open problem, which I think has been forgotten by many of us, okay, is empirically, okay, what people have observed in many, many papers is that if you have two hidden layers, okay, so what I focused on today was mostly one hidden layer. If you go to two, okay, no need to be super wide, okay, and if you set up the step sizes correctly, okay, in particular following like those papers, you always get to the global optimum, okay, very robustly, okay. So here, the words are fuzzy on purpose, okay, reasonably, robustly, because part of the work is trying to give a precise meaning to those for the conjecture to be correct. And this remains open, and I'm sure there is enough brain power in this room to crack it in the following years. Thank you for your attention.
Great, so we've got time for a few questions before the business meeting. So any questions, raise your hand and we'll come around with that.
Can you unpack a little bit your open problem?
Can you repeat?
Can you unpack a little bit your open problem?
I didn't get the, can you unpack?
Can you unpack the open problem? Why two reasonably wide layers suffice to robustly
Oh, you mean
reach?
to more details?
More details.
Okay, so if you, so now, so I go backward a bit, you go forward, but now I go backward. Yeah, this one, okay? Two hidden layers, okay? So you let that layer and that layer go to infinity, but not too large, okay? And can you show that gradient descent gets to a global optimum? What we have shown with Lenaik is that if you just do one hidden layer and this one goes to infinity, it's fine. But the issue is that there are instances for which the infinity is really, really large, okay? It's not like 1,000, it's like 1 billion, okay? So the simplicity bias is one instance where although we know that for m infinite it works, it doesn't work with any reasonable m. It's not true if you have, but not true. It's not empirically true if you have two layers. You don't need those layers to be so large to get robustly to the global optimum.
What do you mean by global optimum? Do you mean matching having the
global optimum? I think so. Here, empirical risk getting to zero error.
But isn't that true if you have more parameters than data? The last layer is
no.
enough.
If you have enough parameters in the last layer, yes, but no, you may get stuck. If you know the answer, tell me. We can.
Well, you have a kernel method, right? So if you have enough degrees of freedom in the last layer, you can match.
If you have enough degrees of freedom, but here I want M not to be, let's say, I have 1 million data points. Okay, I don't want to have like a last layer of size 1 million. The goal here, people do this every day. Okay, they train like neural networks with complex architectures. None of them are infinitely wide. They get to zero loss. Why? I don't know.
So how important is stability in your Langevin gradient flow for faster convergence?
Oh, you mean like for the convex case?
Or for the non-convex case? You know, stability is in your process. I'm asking how important is that for faster convergence?
I think so. In the convex case, stability is really an issue, and in fact, you can essentially see those like fast gradient techniques as being very close to being unstable. Okay, so if you take like SAG or Saga, and if you don't take the step size that we propose, if you multiply by 4, it will diverge. Okay, so we are on the edge of stability. Okay, different meaning than usual. We are really close to being unstable. For non-convex, I know there is some nice words on the edge of stability showing that often, if you have like nonlinear models, you may adapt to the local stability and get to situations where you're going to give me a step size. I will tell you how the variations looks like at the optimum. Okay, so this is one work that I know, but apart from that, I don't know.
Yeah, how are they different, the many particle approximation and NTK? I didn't get the difference.
Oh, the difference is no, I'm lost. So the difference is so NTK. The difference in terms of algorithms is just one parameter difference. Okay, so you simply the exact same code. You change the way you initialize the weights, you get a different behavior. Okay, so it's a one difference in the code. Okay, in terms of function spaces, the NTK will be a kernel method. Okay, so it has to be a space of smooth functions which you're using implicitly. Okay, it has to have like a d over 2 derivatives if d is a dimension. Whereas if you do mean field, it's more a L1 norm type of prior. It's a Banach spec which is much bigger and which can adapt to specificity of your data. For example, if your output depends on a single variable, NTK will not find it. We'll be stuck with it, whereas a neural net will find it very quickly. Okay, so there's this adaptivity of the feature learning regime which you don't have in the kernel regime. Okay, and if you say it in those terms, kernel non-adaptive, neural net adaptive, it seems obvious. And the key is that NTK, there's a K in it. So it has to be a kernel method. I love kernel methods, okay? But I believe that the reason why neural nets work so well is because you have this feature learning appearing behind the scenes.
Okay. Francis?
Yeah?
I also have a question about your question. Over here. So if I understand your question, I mean, you are still referring to the over-parameterized regime. Like the overall number of parameters would be more than the number of data points, just not all of them in the top layer. Is that,
you mean my conjecture?
In your question at the end.
Yeah, I think the conjecture, I'm happy to have more parameters. And going back to your comment, you need more parameters for the global fit, okay?
But in that case, how would it help you if we find the global minima? I mean, the global minima is 0. There are going to be many global minima. Even if you could prove this, how would it help you?
Good point, Nati. I think to me, the first step towards, if you get the global optimum, then the question is which one? At the moment, we have a behavior that we see every day, and we don't know why. To me, it is disturbing. Not disturbing. I'm dealing well with myself, but I think it's an open question, which I think we should tackle. Because to me, it is a door to many more things. It's difficult. It's difficult, I know, but it's not a reason not for doing it.
And just to comment, it is an issue of which regime you are in, because in a certain scaling, it would be true because you'd be in a kernel regime and then just by kind of like rank considerations. But
that's why I left fuzzy words. Is you want essentially to have a set of assumptions which are matching a bit what people do in practice.
Right. Yep.
Okay. That's a very good point.
Okay, so let's thank Francis again. And we have the business meeting right now, so there's a bit of a paradox because the lunch is outside in bags. You are allowed to eat it, but not in here. So you have two choices. You can either come to the business meeting, pick up your food and not eat it now, but eat it later, or skip the business meeting and eat the food. I hope you choose option one, but it's your call. So we will see some of you back here shortly. Yeah. So it's basically going to be a presentation.
Super utile comme talk. Merci beaucoup. Ouais. Un gros travail de synthèse, un énorme travail de synthèse sur ce qui existe. Bon, heureusement, toi, tu as la vision d'ensemble, mais je pense que pas grand